for me.
بسم الله والحمد لله والصلاة والسلام على رسول الله وعلى آله وصحبه ومن والاه أما بعد. حياكم الله وبياكم ضيوفنا الكرام في قاعة مركز علوم البحار للندوات، وما زلنا ولله الحمد والمنة ننهل من علم الدكتور كارل كايزر المتخصص في علوم البحار، خاصة في مجال كيمياء البحار وعلاقتها وترابطها مع العلوم الأخرى. Sorry, Karl, I'm speaking in Arabic. Just the beginning, okay?
Sure.
You're an expert in Arabic, yeah?
I'm learning. Getting better.
ورأينا كيف أن الدكتور كارل وهو متخصص في كيمياء البحار أنه يعني لا يعمل في مجال واحد، بل يعني يكون في ترابط بين الكيمياء والبكتيريا والبيولوجي والفيزيكس، فكل هذه احنا نسميها انترديسبلينري. يعني ما يصير تكون دكتور ناجح في الكيمياء او الفيزياء او الجيولوجيا بدون انك يعني تاخذ من كل بستان ورده ووروده. واضح؟ فهذا اللي يخلي الدكتور او الباحث ناجح في مجاله. فدكتور كارل يتعاون مع دكاتره في شتى المجالات. طبعا اليوم الاخير يعني اتحفنا بعلمه من ناحيه المحاضرات، اجتماعات معه بالابحاث في لجنه المناهج مثلا، اخذ جوله على مختبراتنا، وابدا اعجاب امانه يعني اعجاب شديد في قسم علوم البحار وفي نهوضه نحو الافضل ومن علوم الى علوم، وابدا كذلك اعجابه في المختبرات، وان هناك الكثير من الامور والتطلعات، وان المساحه موجوده. نحتاج ممكن القوى العامله المختصه في علم البحار والميزانيات اللي تنهض بهذا النوع من العلوم. واستمع الى كذلك ملاحظات بعض طلبتنا يعني، والتقى معاهم وشاف انه يعني الطلبه كذلك ابدوا يعني مبينوا سعداء في مركز علوم البحار. وانا اتكلم على العموم، لا تضحك يا ابراهيم. سعيد انت يا ابراهيم ولا مش سعيد؟ قول لي. سعيد الحمد لله.
وفي القلب غصة.
ان شاء الله انه مو مني انا يعني، صح؟ ان شاء الله. والبقيه شو؟ يلا لا اله الا الله.
Now I'm curious.
They said, Karl, I said, you met with our students and they seem happy with the department. And you know, I hope you know I'm part of it, you know. So طبعا راح اقرا سيره الدكتور كارل، قد يكون بعض منكم اول مره يلتقيه. دكتور كارل كايزر marine chemist. He is an associate professor at Texas A&M University, where he has been a faculty member since 2012. He has published in Science and over 50 publications in keyword-reviewed journals. He completed his master in chemical engineering at Johns Hopkins University, Austria. His PhD in marine science at the University of South Carolina. His research interest lies in natural element cycling and the global climate system. Specifically, his research applies and refines quantitative molecular level analysis of major biochemical and various biomarkers with the goal to resolve fundamental mechanisms that control the globe. سموحة منكم صوتي رايح يعني من الفراغ. طبعا انا دخلت دورة مغاوير معي من 7 الصبح لل 10 بالليل يوميا يعني. So control global climate cycle of bioactive elements. In addition, his professional interests are interdisciplinary, ranging from behavior ecological of fishes to engineering solution of water quality improvement and risk assessment of contaminants, resistant pollutants, and micro-nanoplastics in coastal ecosystem. He's completed his research in many geographic locations, including the Arctic, you name it, you know. So basically he did a research in every ocean, sea, bay, Kuwait Bay in the future, inshallah, Siberia, China. Are we missing a place, Karl?
No, you got it.
Red Sea, maybe?
Not yet.
Not yet? Okay. Maybe Zamzam water in the future, so we'll cover every... I think I said South China. One of his major achievements is to develop a rapid and sensitive method for the analysis of lignin phenols in the marine environment. So basically, Dr. Karl, as a chemist, chemical oceanographer, he don't just conduct a basic, simple analysis. Actually, he developed the analysis. And all the other faculty members around the world copying, following his path. So we are really glad and happy here at the Marine Science Department to have Dr. Karl Kaiser. I'm very honored to have him. Also, I am very honored that I gained part of his knowledge during my PhD. And I'm hoping one day I'll follow his path as I look up to him. So please welcome Dr. and Professor Karl Kaiser.
Thank you. Thank you so much. It's great seeing everyone again. Can you hear me in the back? Is it okay? Very good. I'm not going to get too close to there because we'll have some coupling. But so, yeah, I've told you a lot already. And so for this talk, I thought, so to make it a little smaller and focus instead of the big ocean, actually at the coastal systems. So moving from the blue ocean towards land and specifically looking at how hurricanes change carbon cycling in these systems. And we know coastal systems are very important for marine life. 90% of marine life depends on it. We have more and more people living in coastal systems. I think the prediction is over 50% in 2100. And like in the US, we have seen more and more storms, flooding events. We have fires. If you open the news and you read every day, there is some event. We have droughts. Europe has a drought. A lot of rivers are very low. So these processes affect these coastal systems. And so it's really important to understand how these events actually affect processes in these systems. And so to kind of reorient you again, I told you a lot about how important the dissolved organic carbon in the ocean is. It's a gatekeeper to CO2 in the atmosphere. At the same time, we also know that on land we have a lot of carbon stored in vascular plants. So these are units in petagrams. So petagrams, 10 to the 15 grams of carbon. We have a lot of organic 1600 petagrams in soil organic litter. And in the coastal interface, so where land and ocean connect, and rivers make that connection. So there's a lot of transfer of material from land to the ocean, and it's being processed and affects biological processes here. And so we need to, and as we have flooding events, storm events, we want to learn more about how this changes the system in this region here, okay? And just to point out that these systems are very important modulators of carbon fluxes. And specifically, if you think about it, they're tiny surface, like per area, they're very small, but they have a measurable, actually a very high impact on CO2 fluxes. And here a global summary shows that they're actually sources of CO2. But it's pretty amazing for their overall size in the Earth system to have a disproportionately large effect on carbon fluxes. And if you look at the processes that occur, they're actually a dream of a chemist. Because if you look, there's a lot of organic matter coming in, there's photochemical oxidation processes, microbial processes, there is flocculation, sedimentation, resuspension, there's primary production, there's export. So there's a lot of stuff going on. And so it's complicated. And you can imagine that a huge storm can have a very large impact on these processes. And so the event I want to talk about is a storm that actually affected me directly. So I actually live right here. And maybe you didn't read, you can't remember the news anymore, but Houston here received over 4 days this much rain. So it was over 50 inches of rain in 4 days. One of the wettest event ever recorded during a hurricane. And what was interesting also that the storm track was very unusual. It was actually, usually storms come up and they move quickly through, but this one actually backtracked, stayed out on the shelf waters. And so this is the Gulf of Mexico. This is Texas here. So this southern United States. But so it backtracked, set out on the shelf, and then moved slowly along. So it's a very unusual storm track. And that was also responsible for the incredible amount of rain that actually was delivered to the system. And so that storm was in August 2017. Category 4, so over 130 miles per hour. Almost 100 cubic kilometers of rainwater over 5 days. Equivalent flow of, Niagara Falls for 15 days. So a very large flow. And if you look at the discharge of the river, so this is normal discharge, and there was this incredible peak. And you could see it in satellite images. I think it's a little dark here, but I think you can see it. So the bay here was entirely filled with sediment, and you could see it all the way out into the Gulf of Mexico, so 50 kilometers out, the flood plume. And so right after the storm, we actually went out and started sampling. So if you look at the calendar here, here's the storm, and so we did a weekly sampling following the storm. 1, 2, 3, 4, 5 trips, and we collected samples along a transect throughout the estuary. Just to point out a few things, most of the water usually comes in through here. And Buffalo Bayou actually is the outflow from Houston that carries, and actually right after the storm there was a lot of contamination coming out. A lot of sewage came out from overflowing sewage treatment plants. And the other main freshwater inflow is from here, Trinity River, then throughout the gateway into the Gulf of Mexico. And so what we did was we wanted to understand the fate of all the flood-derived organic carbon that was coming out from the rivers. And one approach I've talked about already. So we actually can use lignin as a very specific tracer of terrestrial organic matter. And we can use it as a tracer, but we can use it also as an indicator of specific processes. So one is, just before I get into this, just to tell you, so we can use it as a specific source indicator, also of specific vascular plant material. And so we can actually distinguish gymnosperm, softwood, from hardwood. So they have different mixtures of these phenols. We can also separate woody versus non-woody materials. And then we can use specific ratios of these phenols to look at microbial versus photochemical transformations. So microbial transformations affect the ratios of the acid here over the aldehyde for the vanilla phenols differently than photochemical transformations. And we also did, obviously, we measured some total, so dissolved organic carbon, and did some optical measurements as well. And so we can use some of these parameters, obviously, to look at sources very specifically and also transformations. It's a really, really nice tool to look at really the detailed sources and the processes. And then we also measured enantiomeric amino acids because we could use them to divide up actually algal-derived organic matter from bacterial-derived organic matter. And so usually you find the L forms of amino acids only in algae, and bacteria make the amino acids. So it's a very specific indicator of bacterial organic matter. And so those are methods I worked out actually started actually a long time ago, 2005, and as a grad student. And so it's been really a wonderful tool to study carbon processing in the ocean. And so just to give you an idea of how the salinity changed in the bay, and if you look at this, is actually the bay was completely flooded with fresh water. So salinity dropped basically from an average of 25 parts per thousand to 0. It was fresh water. The entire bay basically was fresh water. And we could also see a very dramatic, and it took actually, how long did, 2 months to recover. So over 2 months, the bay was affected by the freshwater input. And what we also found was that out on the shelf, there was also a very large decrease in salinity. So very large freshwater pools that came through the bay and also affected salinity on the shelf. And so just to estimate freshwater volumes, those are basically 10 to the 9 cubic meters. And so looking at where they were coming from, so total freshwater load was 14 times 10 to the 9th cubic meters, coming, a large portion from the San Jacinto, so from the east side of the bay. And those 14 10 to the 9th cubic meter were about 4 times the bay volume. And so just to give you an idea of general distributions of dissolved organic carbon, so this is maybe a complicated plot, but the time point, so time is on the x-axis, and basically the distance from the north to the south following that transect is on the y-axis. And so what we saw is this incredible input of dissolved organic carbon, so about 90 gigagrams, which was similar to the annual DUC load to the bay. So delivery of organic carbon, but is normally delivered within a year in 1 day, pretty much. It's like, and that, just to put it in perspective, it's always, for me, it's always good to put it against the Mississippi Atchafalaya system. It's a very large river. So it's smaller, but still a very sizable portion, because that's a very large system. And but it was delivered in a very short period of time. And then over time, that DUC disappeared. So obviously, that probably was transformed by microbial communities. And if you look at, so here's DUC, and on the bottom plot is lignin phenols. Similar, makes sense. Is terrestrial carbon. And it mirrors pretty well. But it doesn't mirror at all times. So there was something going on. The bay was responding. And I'll show you actually that there was a bloom happening. So the bay responded very quickly and produced additional dissolved organic carbon. And we actually could see that very nicely when we looked at amino acids. So similar plot, kind of the transect. Oh yeah, that's me. And so basically, you could see about, after 2 weeks, big pools of dissolved organic carbon coming in from phytoplankton production. And what was interesting is that bacteria responded, and we could see that then bacteria started producing material after degrading some of the terrestrial DOC as well as the new phytoplankton DOC. So a lot of processes happening very quickly. And so when you use lignin to kind of look at what kind of organic matter sources were coming in, where was that organic matter coming from, we actually saw that most of the organic matter was from softwood, non-woody, herbaceous tissue. And we can do that by looking at these specific ratios of lignin phenols. So here the cinnamyl versus vanilla phenols plotted versus syringyls versus vanilla phenols. So you see that those gray boxes show the end members of specific tissues. And so the gray box here for angiosperm non-woody tissue fit really well what we found in our samples. So it's very nice to, we could fingerprint that material, the source of the material very well. And, as we noticed there was a lot of processing, we wanted to know who was doing what. We wanted to know if the microbes were processing the material or photochemistry was important too. And so we looked at these acid-aldehyde ratios of lignin phenols, and what you could see is and also we looked at an optical parameter which is called the slope at specific wavelengths, and the signal was very clear that most of the degradation was actually caused by microbial degradation. Because based on these parameters, if photochemistry would have been important, it would be in the red box here, okay? And then, so we were, this is a little complicated, so I'm going to go through slow, but I think the main message is that a lot of that terrestrial material was removed very quickly by microbial processes. And the way we determined this was by looking at lignin phenols, and here reported in nanomoles per milligram carbon, so carbon normalized concentration versus the fraction of river water. And if you plot lignin phenols versus the fraction of river water, and if you mixed terrestrial DOC conservatively, so no change, just mixing with marine water that doesn't have terrestrial DOC, you get this relationship. So this is the conservative mixing line. And then as removal happens, the concentration of lignin decrease. And we can then kind of fit that and determine how much is missing. And the reason why this works well is because it focuses on terrestrial DOC. And if you have new carbon coming in, that changes the signal. Because we wanted to know really how much of if you look at change of DOC, it's a net change. You don't know if it's removed, what's removed, and what's produced. And we knew we had a phytoplankton bloom. So we couldn't tell how much was really removed because we had an input as well. But with lignin, we could determine that very quickly. And the result was that 70% of DOC was lost within 1 month. So incredible, quick response of microbial community degrading all these materials to CO2. And so one question was, well, okay, this happens usually, but how does it compare to normal processing of organic matter in these coastal systems? And so this is a plot you might, I don't know if you remember, but this is work I actually took 10 years to do, to actually look at degradation kinetics of terrestrial organic matter in natural systems. And what I found was, and that was published in a 2017 paper, where we basically found that the decay kinetics change for terrestrial dissolved organic matter over time, and it's actually a very nice relationship. And that includes low latitude, high latitude systems, so basically Arctic Ocean systems, Gulf of Mexico systems, other systems across the world. And what was interesting is that the degradation of that flood-derived organic matter was way off the charts. Really different, really much, much more reactive than what we see normally across natural systems. And so basically what we were observing is that storms can actually deliver materials that are super reactive, that are quickly mineralized and produce a lot of CO2 that comes out of the system. And so converted to, so what was removed to CO2 released, we estimated that that number was about 70 gigagrams of CO2. And so, seeing this and wondering, wow, who is doing this? And so we looked at microbial community distribution over the time of the flooding and afterwards. And we saw that there was a pretty big shift of communities that actually so here we saw basically a shift after the storm, freshwater soil sediment communities, so mostly better, so a lot of better proteobacteria, and then it's kind of shifted slowly to more estuarine and marine communities, and specifically cyanobacteria started reappearing. So there was quite a shift in the microbial community right after the flood to 5 weeks later. And what was interesting was we saw that these microbial communities were very well adapted to degrade aromatic compounds. So we saw that, and terrestrial DOC has a high aromatic content, and that's based from the woody materials, the lignin type material that's aromatic. And so it appeared that those communities were very well adapted and could, degrade those new materials that were delivered to the bay very quickly. And then after 2 weeks, we actually saw a shift in the community, and actually photosynthesis started to become more important. And that we concurred with the cyanobacteria. So a shift in the metabolic capabilities of the microbial community. And so to summarize here, what happened after the storm, right after the storm, the Galveston Bay was more or less a pipeline, so the water came in and flushed out on the shelf. But then right afterwards, there was a lot of mineralization. So 60% was within week 1 and 2, and then week 3 and 4, another 10%. So very quick response of the system to kind of transforming that new material right after the storm. And so summary was, so what we saw is that, we saw a very quick, rapid removal of flood-derived dissolved organic matter over 1 month. We think that really that quick processing was related to chemical composition and an active microbial community. And actually the kind of the question we were interested in, so how does an extreme event like a hurricane affect carbon processing in these systems? We saw that this is a very efficient pathway to transform organic matter to CO2. So it could act as a positive feedback. And that's it. Yeah. Thank you. Any questions?
So thank you, Dr. Karl, for this wonderful presentation. And actually, we can see clearly how Dr. Karl used chemical tools to understand environmental processes, mixing, movement, degradation, all of that using chemical tools. And this is how you should conduct a research in the marine environment. You use whatever tools you have, techniques, in order to understand physical processes, biological processes. And you dig in deep on these. And so, questions, please. So we will start with Mr. Yusuf, please.
Thank you for the wonderful.
Can you raise your voice, please?
Thank you for the wonderful. I'm just wondering, because here we don't get hurricanes anymore, but now in the same region that you get the US. But I'm wondering if sandstorms contribute similar results to what hurricanes on the hurricanes do to dissolve organic matter. So, could you shed any light, if you have any experience in dealing with such a phenomenon? Would you say that they would produce similar results, or is that up for grabs, basically?
Yes, it's up for grabs. Yeah.
It's up for grabs.
Yeah. I have never looked at sandstorms and the effect of sandstorms on coastal systems. When I think of it, I think more of like iron delivery as one, or it doesn't seem the sand is very carbon rich, like organic carbon rich, but it might deliver essential nutrients to a community that's, limited. And so,
They are iron rich,
yeah. So, but yeah, it would be interesting to see what happens to the processing of carbon and the response of the system to a storm, like a sandstorm. And maybe, yeah.
Because I think maybe people from the EPA or other places can confirm, but I think we do get algal blooms after sandstorms. I'm not sure about that fact, but seeing as how you got similar blooms or similar results from the hurricane, of course, blooms can come from any factor, not just specifically material deposited from such phenomena, but it's just interesting because we would like to apply such methodology to our area. So that was basically.
Yeah. Thank you.
Any other questions, students? I'll make sure you get bonus. Faculty member, please give them bonus if they ask a question. So, Dr. Anwar.
That's on.
Same guy. The same guy. You want to-
He's ready. He's ready. Go ahead.
So good.
So all the like sediments come from the land, right?
Yes.
Yeah. So that's like does that wash and swash like when sediments go and return to the
So we were looking mostly dissolved materials.
Dissolved.
Yeah, dissolved. Yeah. Yeah.
So
Yeah. But there was sediment too. Yeah.
yeah. So my question is like does like break of a sediment like when we like do we lose more dissolved organic matter in the sediments or no?
No, there was very little like
Lost.
lost to the sediment. Yeah.
Okay, thank you. I think if I ask a question, Karl,
Yeah.
cancel the student's question. No?
No, good question.
Okay. So, Dr. Anwar?
Thanks for the great talk. Maybe you mentioned the microbial group, but maybe I missed it. I just want to know if you are sure that the microbial group are from they flourished after the hurricane, or they are derived from the rivers. They are marine sources, or they are freshwater origin.
So they were basically coming with the floodwaters from soils and freshwater systems.
So they are not in the mostly in the ocean, and they flourished. I'm
Yeah.
not sure.
Yeah.
I'm not sure how we can differentiate that. Also.
Yeah, I mean,
Yeah.
it was basically it's just relative distribution. There was no abundance data, so we don't know exactly what the abundance was.
Okay.
They didn't.
I was expecting to see maybe bacterioditis as well, a group, because they flourish usually after also algal bloom. So I think I did not see them here. Bacterioditis. They can degrade high molecular weight compounds. So I was surprised I did not see them. But maybe they, that's why they are mostly freshwater.
Yeah,
I
yeah.
have no experience. And bacterioditis are mostly
Marine.
third
Yeah.
most abundant group in the
Yeah.
marine. Okay, and another question.
I will ask Jessica that
Okay.
question. Yeah.
Thank you. I have another question, please. So if the microbial degradation does not occur, how does, I want to think about it, how does that will help the carbon cycle? Okay, let's imagine there will be
No decomposition.
no decomposition. Then we will have, then the hurricane will benefit the ecosystem.
Well, it would just move carbon from one
Yeah, or
reservoir to another, but it would stay the
Right.
same
yeah.
because it would stay fixed. So it would be no.
But as you said, the microbial group are respiring most of the carbon. There's no sinking of the carbon. So I think this is bad.
Yeah, so
Yeah.
it's going out. Yeah.
So,
So that's why the title, what we say, it accelerates the carbon cycle because of actually if I go back, that really elevated decay kinetic. That seems to be way different to what we observe normally. That and we have looked at this, because these systems always receive organic carbon from land, so they are primed, they process it. It's known that they process it, but not at that extent as we saw during the first 2 weeks of the hurricane. It was much greater, and this is actually a logarithmic scale. So that's why we actually, and that's where the title comes from, the acceleration. That was pretty amazing to see, this really quick response, much quicker than we see it normally in a river-dominated system.
Questions, please? Another, Dr. Abdurrahman, I think you have a question?
Yes. Thanks for the nice talk. So I kept wondering, what do you think the effect of more intense and more frequent hurricanes in the future on DOC, on the bacterial community? We kept saying, for example, flood-derived organic carbon is rapidly removed, and I was wondering, okay, what's the effect of that on the ecosystem as a whole, for example, and like under more intense and more frequent hurricanes?
Yeah, that's a good question, and I think we're just trying